Hello, hello. Let's do a little math today. All right, so let me get this set up. Move my face down there. Let's do number 1. So consider the equation x cubed plus 3x plus 1 equals 0. How can we show that this equation has a unique solution on the interval from -1 to 1? Well, you might have some bells being rung from earlier in the semester, but if we take the equation x cubed plus 3x plus 1, we have, I mean, it's clearly a polynomial, but another way of seeing it is you have the addition of 3 continuous equations. F is continuous. All right, so what do we do with this information? We're going to apply the intermediate value theorem. What does that mean? That means that on the interval from here to here, the function will take on all the values as it goes from one point to the next. So let's plug in some endpoints and I'll draw a picture of what I mean. So f of -1 is -1 cubed plus 3 times -1 plus 1, that's -3. F of 1 is equal to 1 cubed plus 3 plus 1, it's going to be 5. So if we take the picture, I don't really care exactly what the function looks like. This is definitely not drawn to scale. But if you look at what we have here, we know that since f is continuous, and on this part of the interval, it's -3. On the other end of the interval, it's 5. It has to start down here and take some kind of journey where it has to bust up through the x-axis here and go to 5. This value here we will call C. And at this point, due to IVT, f of C equals 0. Let me make a new page really quick. All right, so we have this solution right here, but why is it unique? Let's suppose that there's two values, f of x1 equals f of x2 equals 0 on the interval -1 to 1. Well, at this point, we can use a new theorem, which we just learned, Rolle's theorem. So what does Rolle's theorem tell us? It tells us there is a point C inside of the interval, -1 to 1, such that f prime of C equals 0. Drawing a picture of what something like that looks like. You got to have some kind of, you got to have some kind of peak right here. Okay, so let's take that bit of information and let's consider the derivative of the actual function f prime of x, which is, this is an old hat problem to us at this point, 3x squared plus 3. Well, if we set that equal to 0, 3x squared plus 3 equals 0, we get x squared equals -1. I subtracted the 3 and divided by 3. And then we get x equals plus minus I. And that tells us there is no solution when we have two variables that equal 0 when taken under the function value or whatever. So since we have a contradiction, there can't be more than one. So the solution that we have here from the IVT is unique. All right. Number 2. What do we got? So on the interval AB, which is equal to the interval 0 to 1. We want to find the values C that satisfy f prime of C equals the average slope if the function is x to the 2/3. Okay, so when I see these problems and I know that I have to use the mean value theorem, the first thing I do is I just take the derivative just right off the top, go ahead and get that piece of information on the board. So here's 2/3 x to the negative 1/3, and that's going to be 2 over 3 times the cube root of x. Now, we know by the intermediate value theorem that, well, let me write that down. By MVT, there exists a C in 0 to 1 such that f prime of C is equal to f of B, which is going to be 1, minus f of A, which is 0, all over 1 minus 0, which is just 1. So let's plug in C, and we'll get that this expression right here is equal to 2 over 3 times the cube root of C. All right. Let's just flip-flop things around a little bit. No harm, no foul on the right-hand side. On the left-hand side, we'll get 3 times the cube root of C over 2 is equal to 1. And now we'll have 3 times the cube root of C is equal to 2. Cube root of C is equal to 2/3, and then C is equal to 2 cubed over 3 cubed, which is 8 over 27. That value is approximately, hold on, I had to put it in a calculator because I'm not as cool as some people. That value is approximately 0.3. Check it out, check it out. That is definitely within our interval from 0 to 1. All right. Let's do number 3. Basically the same question. So let's go ahead and slap down our derivative. We get f prime of x equals 1 over 2 times square root of x minus 1 times the derivative of this inside part, which is just 1. All right. Now, we know that there exists an f prime of c that is equal to f of b, which is going to be root 3 minus 1 minus f of a, root 1 minus 1, all over b minus a, which is going to be 2. So now we just do our plug and chug and work out some algebra. So we get, plugging in c here, we get 1 over 2 times square root of c minus 1 equals square root of 2 over 2. All right, let's just flip everything. Nice average algebra. 2 times the square root of c minus 1 is equal to 2 over root 2. Now, divide both sides by 2 and square everything. 2 steps in 1. We'll get c minus 1 is equal to, divide these 2's first and then square 1 over 2. Then add the 1 and we'll get c is equal to 3/2, which is 1.5, which is definitely in our interval from 1 to 3. All right. Moving on. Number 4. So we want to show that g of x equals 2 to the x has slope 1.5 somewhere along the interval 0 to 2. Okay, So we're talking about average slope. We're talking about intervals. Clearly, this is an NVT problem. Jesus, what is that? So we're going to use NVT. It doesn't matter so much at this point what the derivative is. What we're going to do here is we're going to go ahead and take the average slope just to see if we get something that we like. So one moment, I got a few notes here. What is the average slope? We're going to get f of b, which is 2 squared, minus f of a, which is 2 to the 0, over b minus a, which is 2 minus 0, is equal to 4 minus 1 over 2, which is equal to 3 halves, which is, whoa, 1.5. Well, we have a continuous function. We know what our average slope is. So now we can invoke the mean value theorem and say that by NBT, there exists a C in the interval 0 to 2 such that G prime of C is equal to 1.5. And that's it. That's how you do these kind of problems. This was number 4. All right. Number 5. All right, same deal as number 2 and 3. So let's take our derivative. F prime of x here is 1 over x minus 1 times the derivative of the inside part times 1. I know that's pedantic, but it's always good to keep it in mind. Now we know that, oh, it's also important to keep in mind that ln of x minus 1 is continuous on 2 to 4. Make sure you pay close attention to those domains there. So by NBT, there exists a C in 2 to 4 such that f prime of C is equal to f of B, which is going to be ln of 4 minus 1, which is 3, minus f of A, which is ln of, wait 1 second, I need to double check something. Okay, sorry. Yeah, so f prime of C is equal to ln of 4 minus 1, which is 3, and then f of A is equal to f of 2 minus 1, which is ln of 1, over 4 minus 2. So what do we get? Let's go ahead and plug in this f prime of C, which we can find up here. We get 1 over C minus 1 equals ln of 3 minus 0 over 2. Let's do a little flipping action. C minus 1 equals 2, not 21. Silly me. Equals 2 over ln of 3. And then C equals 2 over ln of 3 plus 1. Now, that's kind of a mean value to plug in, but fear not. I have plugged it in for you, for I am a merciful TA. This is 2.8. All right. Oh, quick note, 2.8, clearly in our interval from 2 to 4. So, nice stuff. All right, number 6. Does this function satisfy the hypothesis of the mean value theorem? And the way to check these problems is to take the derivative and see if there are any issues. So f prime of x is going to be 2 over 3 times the cube root of x. That is right, yeah, you minus 3 over 3, you get negative thirds, yeah. All right, so what's the immediate problem here? We know that the element 0 is inside of -1 to 8. So that is a problem because that means the function is not differentiable in this open interval. So we cannot apply the mean value theorem. All right, number 7, same deal. We'll take a quick derivative, just some power rule nonsense right here. 4/5 over the quintic root of x. I believe that's the quintic root. However, check this out. In BT, we're only curious, or we only care about the open interval from 0 to 1. So 0 is not in there. We have no problems. We can apply the mean value theorem here. All right. Time for a word problem. So in the future, when you see questions like these, typically physical functions that have to do with real world problems, physical problems, are continuous and differentiable just by assumption. That's how we work with them. That's how we mess with them. Turns out it's a really great way to approximate reality, which is kind of wild if you think about it. So what do we have? We have that it takes 14 seconds for a mercury thermometer to rise from -19 degrees Fahrenheit to 100 degrees Fahrenheit. Okay, so we have an interval from 0 to 14 seconds. We have a function which is evaluated to be we have a function which, for an element x in here, that's going to equal the temperature. We're not exactly sure what this temperature is, but we know that the function is continuous and differentiable on the closed and open interval respectively. So let's talk about endpoint values. We know that f of 0 equals -19, and we know that f of 14 equals 100. All right. These are enough ingredients for us to use the mean value theorem to figure out this problem. So we know that there exists a c in 0 to 14 by the mean value theorem such that f prime of c is equal to f of b, which is going to be this value right here. This is our b, this is our a. F prime of c equals f of b, which is 100, minus -19. Be very careful, this could mess you up in the future. Let's throw down some units too. So we'll say this is 100 degrees and 19 degrees, -19 degrees, and then this is 0 seconds to 14 seconds. All right. So we get 100 degrees minus -19 degrees over 14 seconds minus 0 seconds. Then what do we get? We get 119 over 14 seconds, which is going to simplify to 17 over 2 degrees per over seconds. Just divide both sides by 7. And then this is exactly 8.5. Yeah. 8.5 degrees per second, which is the answer that we're looking for. We had to show that somewhere along the way that the rate of change of the mercury was 8.5 degrees per second. Here it is, using the mean value theorem and teasing out details from what we know and approximating reality by using continuous modeling. So let's do another one. So A police officer sees a red car pass mile marker 42 at 1:04 p.m. A second police officer sees the same car pass mile marker 65 at 1:19 p.m. The second officer pulls the car over for speeding, even though the driver had slowed down to below the speed limit. How did the second officer know the driver was speeding? Well, apparently the officer knew a half a semester at Cal 1, which is pretty cool. So let's do our function from 1:19 p.m. Oh, from 1:04 p.m. to 1:19 p.m. 15 minutes elapsed. So let's make a time interval from 0 to 15 minutes, or 0 minutes to 15 minutes. And then we know that at these endpoints, our function f of x equals distance, that f of 15 minutes equals 65 miles, and f of 0 minutes equals 42 miles. This is better stated as mile marker. And then subtracting them is going to give us our distance. So mile, 65 mile marker, 42 mile marker. All right, not the best notation, but it's getting the job done. We know what we're talking about. At least I hope we do. All right, so we have our ingredients for the NBT. So there exists a C in the interval from 0 minutes to 15 minutes, such that f prime of C is equal to 65 miles, oh Lord, you know what I mean, minus 42 miles over 15 minutes minus 0 minutes. Miles. All right, let's do a little simplification. So 65 minus 42 is 23. 23 miles per 15 minutes. You might not know what that is, right off the bat, but it's pretty fast. So if we multiply the bottom side by a fancy 1, this is just some high school unit conversion here, 1 hour per 60 minutes, we get 23 miles per 0.25 hours, which is going to be equal to 92 miles an hour. So unless the speed limit is 100 miles an hour, which I doubt, he definitely broke that speed limit. So there you go. Thanks for watching.